right, so the last thing I wanted to do in chapter 13 is an important type of problem in physics. It's called the central force problem. And what we're going to do in this particular type of central force problem is concentrate on gravity. And think about a situation where you have perhaps a satellite orbiting the Earth, and of course it's under the influence of gravity. So that's the central force. So a central force is a force that basically always acts towards a central point, and it would be a radial force, and so gravity is an example of that. So what I'm going to do is I'm basically going to show you how you can solve the differential equations that come up for a central force such as gravity using polar coordinates. Polar coordinates make sense because of the way the object moves and because the force is along the radial direction. I think you're going to find that some of this derivation varies a bit from what you see in your book, but I'm going to stick with what I got. So we're going to start off with the idea that our object right now, when it's at its initial position and all right, sorry if there was a little glitch there, just got interrupted. So, okay, so what we're looking at is we're going to imagine a satellite that is orbiting the Earth, and we're looking at its initial position. We're taking its initial position to be either its closest approach or its furthest approach, because at that moment its velocity is totally perpendicular to the radius. That's what they're trying to show right here with that angle. And then, of course, as the satellite travels through the orbit, we're going to follow it using polar coordinates, using the radial unit vector and a tangential unit vector. And these are older slides, so the unit vectors might look different from what we're used to. So the force that we're looking at is the force of gravity, which we can write as minus big G, mass of the Earth, over the radius squared, where the mass without the subscript would be the mass of the satellite. We're going to write this just to get rid of some terms in terms of the acceleration of gravity of the Earth at its surface. So if we let G be equal to big G, the mass of the Earth, over the radius of the Earth squared. So you can see that if we did that substitution, we would end up with this expression. So now we have the sum of the forces in the radial direction equal the mass of the satellite times its radial acceleration, and the sum of the forces in the tangential direction would equal the mass of the satellite times acceleration in the tangential direction. Now, it only turns out that there are only forces in the radial direction, so for the tangential equation, the mass times acceleration has to be equal to 0, because there are no tangential forces like for this problem. It's all it's a central force problem, so it's along the radius. So if I rewrite these two equations using my polar expressions for acceleration, for the first one, the radial, I'm going to write minus m little g, acceleration of gravity. So that's my force, and that's equal to my mass times my radial acceleration, which is the second derivative of r with respect to time. That's our r double dot, minus r theta dot squared. So we're just going to write it out. So this is the radial expression. That's a differential equation. In the tangential direction, our forces are 0, and that's going to be the mass times the tangential acceleration, the theta expression for acceleration, which is r times theta double dot plus 2 r dot theta dot. And so that's the transverse equation. That's the transverse differential equation. So we're going to look at that equation. Because it's equal to 0, it's easy to sort of manipulate it. And we're going to get rid of the mass because we don't really need it. Sorry, I should have a plus up here. And actually, if you look at this, it's probably not immediately obvious, but if you look at these two terms, it actually looks like you're finding the derivative of a product. And so if we can actually convince ourselves, oops, sorry. If we took the derivative of r squared times d theta dt with respect to time, we would, and then divide it by r, we would actually get this term, well, this whole, both of them added together. So, and that this equals 0. And so that's an important relationship. So go to my next screen. So I'm just going to rewrite it. So the differential equation for the transverse motion actually leads us to a rather important revelation, because of the fact that we're basically saying the time derivative of this expression is equal to 0. That's actually saying that the angular momentum is conserved. Because remember, if a time derivative of some quantity is equal to 0, that means that the quantity is constant in time, which is another way of saying that it's conserved. So we're saying r squared d theta dt is equal to a constant. We could express it as r squared omega or r v theta. And this term is actually the angular momentum over the mass, which is r cross v. And so we had initial values of r naught and v naught. So we can say that r naught v naught is equal to r squared d theta dt. And so we can rewrite d theta dt as r naught v naught over r squared. So what we're trying to do is simplify some stuff. So we're going to substitute this into the radial equation. And if we do that, this is our radial differential equation. And what we've done here is we're substituting in, this term originally was r times d theta dt squared. And so we've made that substitution. Now, we want to make a change of variables. What's happening here is that we have the relationship of r with respect to time, but what we really want is we want an equation for the path. So we want r and theta we want some sort of differential equation that makes a relationship between r and theta, and because that's how we can get the equation for the path of the object. So we want to make that substitution. And so we're going to introduce a new variable, u equals 1 over r, and basically now we have to think about how we can rewrite that term. So for instance, dr dt is something that we have to work with, and so that would be the same as taking the time derivative of 1 over u, because r and u are inversely related, which would be equal to minus 1 over u squared du dt. But now we're going to use the chain rule to try to get rid of the time and write things just in terms of, in this case, in terms of u and theta, but then to also get it into r and theta. And remembering, we found previously d theta dt can be written as r naught v naught over r squared, so we have to remember that. So dr dt can be written as minus 1 over u squared du d theta, and now we're going to make a substitution for d theta dt, but we'll write it as u squared r naught v naught. And so this can actually end up to be as minus du d theta r naught v naught. So our u's disappear. So this is one substitution that we can make. Anytime we see dr dt, we can substitute it with this. We have to also get the second derivative. We're going to use the chain rule. And so what we've done successfully now is we have found expressions for the first derivative of r with respect to time. We've been able to write it in terms of u and theta. Remember, u is essentially going to be r, but we're just using this to get our change of variables. And then we've also been able to write the second derivative of r with respect to time in terms of u and theta. So what we're going to do is we're going to use these in the radial differential equation, and so we're going to get minus g re squared over r squared, which is also can be written as minus g re squared u squared is equal to minus u squared r naught squared v naught squared d squared u d theta squared minus r naught squared v naught squared over r cubed. Sorry, we got a little bit of mixing of our variables. And so putting it all together. Still looks like a mess, but what we can do if we isolate this, and what we've done is we've rewritten this after a lot of work that you probably wouldn't have thought of doing. We're rewriting this differential equation in the radial direction in a much simpler form, where it's just simply a second order non-homogeneous differential equation. So, and it's actually a relatively familiar one. So let's go to the next page to take a look at this. So if it was, so I want to rewrite the differential equation. If it was homogeneous, all that means is the right-hand side would be equal to 0. And honestly, then actually it would have the form that, it might not be immediately obvious, but it would basically have the form of the simple harmonic oscillator. It's just that instead of time, we would be looking at u and theta. And so the solution to the homogeneous equation is, we're going to write it u sub h would be a sine of theta plus b sine of theta. And then from differential equations, if we look at the non-homogeneous solution, that's solution would be adding this plus some constant, which is essentially the constant that we see on the right-hand side. So our solution can be written as a sine of theta plus b cosine of theta plus g r e squared r naught squared v naught squared. And so if you might remember from differential equations, we can use the initial conditions to find our constants. And basically our initial conditions are that when theta was 0, r was equal to r naught, and so that means u would be equal 1 over r naught. Vr was 0, and v theta was equal to v naught. So if we substitute that in, let theta equal to 0, the term for the sine term, where it has the a, will disappear because sine of 0 is 0. We get 1 over r naught, because that's u, will be equal to b, and the cosine of 0 is 1, plus GRE r naught v naught. Both of those are squared. And so from that, we find that b is equal to 1 over r naught minus g RE squared over r naught squared, v naught squared. And then, since dr dt is 0, which is Vr equals 0, say du d theta is equal to 0, which is equal to a cosine of theta minus b sine of theta. evaluate at the theta equals 0, we would get A equal to 0. So basically this allows us to find, we have found A and B using initial conditions. So our equation for our solution is going to be this, 1 over R naught. So this is our B times the cosine of theta plus the constant. This is where we're going to skip a couple steps because the algebra is a bear. If we let this new term, eccentricity, equal to R naught V naught squared over G R E squared minus 1, we can rewrite our equation in terms of R and theta. We can write it as R over R naught equals 1 plus E, or 1 plus E cosine theta, where E is called our eccentricity. Basically, this is how Newton figured out that this solution is like all the conic surfaces. Like basically, if you take a cone and you slice it different ways, depending on the eccentricity, you have different curves that you can create. You can create a circle where the eccentricity is 0. If the eccentricity is somewhere between 0 and 1, it's an ellipse. If the eccentricity is equal to 1, you have a parabola. And if it's greater than 1, you have a hyperbola. And so basically what this says is that for the central force problem of an object moving under the influence of gravity, based on its eccentricity, it's going to follow one of these paths. For the planets, the eccentricity is between 0 and 1, but it's actually very close to 0, so it looks very circular, but they're actually elliptical orbits. And it was kind of a big deal to figure this out. So in a sense, we've shown how you could go about solving that particular problem and coming to the solution that for planets or for satellites orbiting a planet, that the paths are going to have to be some sort of conic section, but it's all going to depend on what the eccentricity is, which is going to sort of go back and depend on what the initial conditions were, how fast was it. So let's go and answer quickly to an example. Sorry, I didn't know how much how many these would take. So essentially, let's look at this example where we have an object with an orbit, and we're going to say we're going to use this expression for its, figure out how R depends on theta. And so we know that R naught is 6,700 kilometers. Initial velocity, we're not sure of. We're going to try to figure out. And the maximum, R max, this is when theta equals 180. So we started off with the R min, was its R naught. It was at its closest approach. But what is it when it's furthest? You know, that we say that that is going to be equal to 13,400 kilometers. So we know those two values. So what we can do is we can say R max is equal to R naught times 1 plus epsilon. And then it would be 1 minus epsilon because we're letting the angle theta be 180. So we can write 13,400 over 6,700. So it doesn't matter that it's in kilometers since we're dividing the terms, is equal to 1 minus epsilon, 1 plus over 1 minus epsilon. And that's going to be equal to 2. And so from that, we can find that eventually the eccentricity is equal to 1/3. And then we're going to set that equal to R naught v naught squared over g re squared minus 1, and we can actually then solve for v naught. And I'll let it to you to do that math to see if you can figure it out. It should be 8,900 meters per second, so you can try it out and then see if you get the correct answer. I know this was a lot, and I know it's kind of boring, but it's kind of good to see the technique that was used to make this, to sort of get to this answer. Maybe appreciate the math if nothing else, because Newton figured this out way back when. And that's going to be it for Chapter 3.